So if we have a resistor over here connected to a battery, there will be some current running through the system. And well, this point and this other point, there is a potential difference between those 2 points A and B. And that potential difference is, let's just call it V. Now, the total number of charges that is going from A to B per unit amount of time is nothing but the current. And this is nothing but the power of the resistor. So if you have one charge, the amount of work done or the energy lost will be just V times 1 coulomb. If you have 2 coulomb, V times 2 coulomb, that is the work done. Power is the work per unit time, so it's the V times charge per unit time. But charge per unit time is nothing but the current. Now this power is basically, if you remember how we discussed the resistance. Resistance is due to the collisions between the charge carriers and the atoms. So I have these charges, electrons, let's say, that are moving quite fast in random directions. They gain some velocity due to the applied electric field. They gain an electric field. They gain some velocity, but then they collide with the atom and losing that velocity, that additional kinetic energy. Then that kinetic energy goes to the atom. So on the average, the atoms of my resistor start to acquire some additional kinetic energy. And that is basically what we call they acquire kinetic energy. They are not able to move. They are not able to go around, but they can still vibrate. Now they vibrate in random directions more energetically. Well, that random motion is what we call the heat energy, or a measure of which is the temperature. So this power, V times I, is used in heating the resistor. Well, of course, this power should come from somewhere. So due to these collisions, the charges are constantly losing energy, but there should be something else that is doing work. Well, there should be some force. The force acting on a unit charge, let's say, some of it will be inside the battery. This is the force of the source. Well, inside the battery, whatever is creating this current is just forcing the charges to go from one place to the other, from one terminal to the other terminal. So that is what we can call Fs. But there will be also it's possible that there will be some accumulation of charges here and there also on the wire. Let's say that is the plus F. This is just the electric field, basically. Let me just call it E. That's what it is. Now, the work done by this force, let's just imagine a unit charge moving around my circuit. So this is the work done on my charge. Well, this is the work done on my charge, and that is the energy that my charge loses. But you see, this E is created by the point charges accumulated here and there. But the integral of this electrostatic electric field around any closed loop is just 0. So this is basically Fs.dl. This is the work done on my charge inside my source, whatever the source is, so that the charge goes from a lower potential region to a higher potential region. This is what we call the EMF. The origin of this force can be whatever you can imagine. If you can, let's say, it can be chemical, or if we can someday manage to build some microscopic devices which just pick up the electrons from somewhere and move them to some other place, it can be that force or whatever you can imagine. But whatever the origin is, that integral is how we define the EMF. Okay, EMF, you will almost never see it written explicitly what it stands for, but the explicit name is electromotive force. Well, electromotive, it is what causes the electrons or the charges to move around in a given circuit. That is why it's called the electromotive. But it's not a force. It's not really a force, you see. EMF is kind of a work. It doesn't even have the correct units. Yes? Because E dot dl around any closed loop is 0. Because that E is the electric field created by some static charges accumulated at various points in my system. That is how I define the EMF. You see, I just consider one closed loop. The charges, let's say, start from this point. They make one full turn and come back to the same point. During this time, they lose that power. There should be some other source that is doing work on my system. And sure, but I mean, that doesn't turn out to be a useful definition. I mean, if the charge is moving from here to there, of course, the work done on it will have some different expression. But it's not that useful. Furthermore, in the resistor, there is some electric field, for example. That is something what we take into account. That is what creates that V. But that kind of disappears. That E disappears when we take this loop integral. Because of this property, the loop integral of the electrostatic electric field is always 0. Well, something that will be of more interest for us is what we call the motional EMF. Let's imagine a region of space where we have some magnetic field. Let's have such a circuit. This is our lamp. And let's put a rod over here. And let's assume that this rod is moving with a velocity v at a given instant. Well, if you consider a given charge, what will be the direction of the force acting on it? An electron, let's say. Down, the electron is negative. So this will be the motion of the electron. Well, the current will be going upward. That's the direction of the current. Well, now it's not anything chemical that is creating. This will be the source of my EMF now. And the force per unit charge, this is how I define my EMF. This will be just VB times, well, let's just call this LVBL. Do you see it? Well, let's give some names, A, B, C, D, etc. Well, the Fs.dl, this is the force due to the source that is creating the EMF. Well, this is just from A to B, the magnetic force, that dl. Again, this small f is the force per unit charge. So this is V cross B dot dl from A to B. Well, V and B, they are both perpendicular to each other. They are assuming they are constant. Well, they are constant along the road. This is equal to VB times L. What is doing the work? Obviously not. It's not the magnetic field that is doing the work. Well, you can say that if the rod is moving at constant velocity, in that case you should be, well, there will be a current running upward. But if there is a current running upward, that means that the magnetic field will exert a force on the rod which will be in the opposite direction. But so that means the velocity, if the velocity is constant, there has to be some other force balancing the magnetic force. So you should be kind of pushing it. And that the force that is pushing is the one that is actually doing the work. If there is no force, but you just send the rod freely, in that case, the rod has a kinetic energy. The rod is moving with velocity v. The current builds up. There is an opposite force, so the rod slows down. The kinetic energy of the rod is basically transferred to the kinetic energy of the charge carriers. So in this case, it is the rod that is doing the work and hence losing energy. If there is no external force, it will just slow down. And obviously, it's not the magnetic field doing the work. Well, we can write this in a different form. Let's say this distance is x. Or let me call this distance x. Then v is nothing but dx by dt. Plus or minus? Minus. Because if v is positive, then x is decreasing in time. That is dx by dt is negative. So v is equal to minus dx by dt. So the EMF is equal to minus dx by dt times BL. This is minus d by dt, b times L times x. Well, you see, L times x is nothing but this area over here. Area is just L times x. So this is equal to minus d by dt, b times A. This is the area, not the vector potential. But b times A is nothing but the flux. The magnetic flux divided by dt. Where this phi b is equal to b dot dA, ds. So if there's a change in flux, then there will be an EMF created. But keep in mind, only part of the rod, the other sections are all at rest. They are not moving. Well, there's no magnetic field over here, but since they are not moving, it doesn't really make any difference. So it's only this rod that's moving in this case. Well, now there seems to be a problem, though. On the other hand, we have F dot dl around the closed loop, which we defined as the EMF. On the other hand, we have minus d by dt b dot ds, which we defined as minus the time derivative of the flux. Well, there is this direction of the loop. There is also this direction of the area vectors. They are arbitrary. I mean, you can choose your loop in any direction you like. You can choose your surface area element in any direction you like. The only important thing is that they have to be consistent with each other. And the consistency condition is, again, your right hand. Take any closed loop, curl your fingers in the direction of the loop, your thumb points in the direction of ds. So if we go back to this example over here, our loop is has this sense. So the direction of ds is in the direction of B, so the B magnetic flux is positive. That's why here we could identify the magnitude of B times the magnitude of A as the integral of B over the area element. Because if they would be pointing in opposite directions, then this would be minus B times A. Now, of course, this is a result for a simple rectangular planar loop. But we can even generalize it to an arbitrary shape. Let's just imagine any shape, loop of an arbitrary shape. We will be deforming it with time. Well, this deformation, after deformation, let's say it takes this form. And you can just think of any deformation you like. So this segment over here basically becomes the segment over here. It is just displaced by dr. At that point, let's say there is a B field. So the change in flux is basically, let's say we have an area element over here. Now let's say this is a length dl. Now what is that area?
dn,
That ds is equal to dl cross dr. Or dr cross dl, sorry. Well, you see my loop is kind of going clockwise, so my ds vector is kind of into the screen. That's my ds vector. Now let me write it in this form.
Hocam şu B'nin yönü neresi?
I don't know, I don't care. We will just write an expression that is valid in general. Now the change in the flux due to that very small element in this time will be just B dot dr cross dl. Or, let me write it in this form, divided by delta t, the change in the flux due to that very small element within this amount of time delta t would be B dot dr over dt cross dl. Which is the same thing as dl dot b cross dr by dt. Well, dr by dt is nothing but the velocity of that very small segment. So this is the velocity of that segment. So this is just minus dl dot f. So d by dt of that very small segment, the change in the flux due to the motion of that very small segment is equal to minus that thing. If you just sum over all these small segments, you get the total flux. But this is nothing but minus EMF. Now what did I do? Let's repeat this. I have this wire of an arbitrary shape. It doesn't even have to be planar. And its shape changes in a very small amount of time, delta t or dt. Well, its shape changes because all the segments of this wire is now at a different position. I just looked at one of these very small segments, and now it started from here and it shifted over here by dr. So the flux enclosed by my loop did change now due to that motion. And the change in the flux due to that motion is nothing but the flux in this area. Now that area vector, I can just easily write it as dr cross dl. This also gives me the direction of that area vector. That is a very small area. So if I multiply it with the B field, take the scalar product, this gives me the change in the flux due to that area element over there. Since I'm using the vector notation with scalar products, etc., I don't even need to know what is the direction of B. Whatever the direction of B is, this scalar product gives me the change in the flux enclosed by my loop due to the motion of this segment from here to that segment. Well, this motion happened in a time delta t or dt. I divide by delta t or dt, whichever one you prefer. So this is what I obtained. This is that very small flux due to that motion. This is the rate of change of that flux due to the motion. It is given by this expression over there. Now, there I use this property. If you have any three vectors, A dot B cross C, this is equal to C dot A cross B, which is equal to B dot C cross A. You can just permit them, all these three vectors. So that is what I did. So that scalar product is equal to the scalar product of dl with B cross dr by dt. Now, dr by dt is the velocity of that very small segment. So that segment is moving. There is a force acting on the charges in that segment due to the magnetic field, which is not doing the work. And so this is the velocity of that segment. B cross V, or V cross B, would be the force per unit charge. So if I change their position, I get a minus sign. So this in square brackets is nothing but minus the force per unit charge in that segment. So what I obtain is the rate of change of flux due to that very small segment is equal to minus dl. dl is the vector along that segment, scalar product with the magnetic force at that point due to its velocity. Now I need to sum the changes in the flux due to the motion of all the segments. But if I sum the changes in the flux due to all the segments, I get there's also this time derivative, I get the total change in flux, the total rate of change of flux. So this is the flux in that very small area. I just sum it for all the segments, so that gives me the rate of change of the total flux enclosed by my loop. I need to sum all the segments. If I sum all the segments, I get minus dl times the magnetic force acting on each one of the segments in my loop. But this is nothing but what we call the EMF. Or with that minus sign, minus EMF. So although we started by a very small loop, a very simple loop, not a small one, a simple one, simple rectangular shaped loop, to obtain this result is valid for a loop of any shape that you can imagine. And this is what we call the motional EMF. This is in fact what is generating the electricity. We use the water, we burn natural gas, we burn coal to obtain some motion. And that motion is then converted to electricity that we use in homes. Well, you see, not really. Let's look at the microscopic view. Okay, so we have this segment of conductor. Let's say we have a magnetic field. Now, this segment of conductor is moving up. There is a current running in this direction, let's say. Now, if you imagine one charge over here, let's say a positive charge, not the electrons, it is moving in this direction. So that's the direction of the motion. And the force that is exerted on it is, let's say in this direction. There's a magnetic force acting on it. So it will do such a motion. Eventually hitting the boundary of the metal. And then it will bounce back. And it will again hit the boundary. The force will be always perpendicular. So it will be just making such a motion. So on the average, it is moving in this direction. That is what's creating the current. The force, the magnetic force is always perpendicular to it. But when it hits the boundary, the metal exerts a force on it. Or it exerts a force on the metal, slowing the wire. I mean, the velocity of the wire is upward, so it just slows it down. But the work done by the wire itself or by whatever external force you have, its magnitude is exactly equal to this one, F mag dot dl.
Ama diğerinde F magnetik her zaman dik değil mi?
Well, you see, this F, when we are evaluating this, the magnetic force, we are only taking the perpendicular component of the velocity. So the actual velocity of the charged particles is actually this one. But we are not using this velocity to calculate the magnetic force. We are using this component. And this component of the velocity gives a magnetic force. And if you use that expression to calculate the work, that is exactly equal to the work done by the external thing, whatever it is. It is just the equality between those two things which allows us to write it as if it is the magnetic force that is doing the work. But if you look at this picture, this microscopic picture of the forces act and how the current is created, you see the force is always perpendicular to the charge. The magnetic force is never doing the work.
Let's assume we induced an EMF of epsilon. Each 2 points on the loop a voltage difference of epsilon. So
No 2 points. You see, this is not, EMF is not a voltage difference. You see, already, I mean, one reason we are writing it, the EMF, in this form. Well, okay, so let's do a couple of different things. We wrote EMF in this form to start with. Okay. So if this is localized to a very small portion of the loop, then you can kind of say that, okay, the rest of the loop has a potential difference EMF. If this is located to a very small region. But in this example, the source force is not located to a very small region. It happens everywhere.
So if there is a current must be flowing from high potential to low potential.
Well, let's see. Suppose we have this circuit with a lamp which has a resistance R. Okay? And it's in a region where there's some magnetic field, not necessarily uniform. And it is moving or as deforming, let's say. Oops. This loop will be deforming. There will be an EMF generated. This is the work done on a unit charge as it's going around one loop. But at the same time, I know that this will be equal to I times R. This is the power lost per unit charge. No, sorry, V times I. No, sorry. I times R. So we can still calculate the I. Across the resistor, I can kind of say that the potential difference is I times R. But we will see, let's say this week, that talking about potential difference kind of loses its meaning.
Peki şöyle şey olamaz mı? Hani şu noktanın şuraya gitmesini sağlayan şey potansiyel diferans diyemez miyiz?
Well, let's say EMF is, okay, let's write it in a more proper way. That is, EMF is the work done per unit charge. So if you send, let's say, Q charge per unit time, that is epsilon I is the total work done on your system as it is carrying a charge. It's the power delivered to your current as it is going around your loop, which should be equal to, by energy conservation, V times I. This is the power that the resistor dissipates. So now this time this is the energy conservation. Well, you see, when we were talking about the potential, we said that it doesn't make any difference which path you take to evaluate the potential. But here it does make a difference. So in that sense, we cannot really identify it with a potential. Of course, if Fs is localized, in that case, you can still talk about the potential out of your source, not in your source, but out of your source. You can still talk about the potential. It makes sense. But if Fs is not localized like in a generator, if Fs is localized like in a battery, then we can talk about the potential differences across points. But Fs is not localized like in a generator, then talking about potential differences, you have to be a bit careful. You can still make use of them, but it might be problematic. And just a last word. Well, you see, this form of defining the EMF will also be reference frame independent. You see, this way of looking at it, okay, this is moving with a velocity v, is kind of a reference frame dependent quantity description, because v depends on which reference frame you are in. So if you just start moving with the rod, then the rod is not moving. But still, even if you go to another reference frame in which moves with a velocity v, the rod will be at rest, but these magnetic field lines will be moving, so the flux will still be changing with the same rate. So this d phi by dt, this quantity is independent of which reference frame you are working at. So that is kind of nice. And that we will make use of. Okay, any last questions? We have a lecture tomorrow morning. I will pick it up from here and continue tomorrow morning. So see you tomorrow morning.
Peki bu non-inertial reference frame olsa o zaman farklı şeyler olur.